Is there a pattern here? Recognizing patterns and sequences. We're in Module 1. This is Topic 2 and the first lesson in Topic 2. Warm up. Write the next 3 terms in each pattern and explain how you generated each term. Number 1. What do you think this pattern is? Do you notice? January, February, March, April, May, June, July, August, September. So we're going to have October, November, December to complete that pattern. They are the first letters of each month. Number 2, let's look at the pattern. Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. They are the first letters of each day of the week. Number 3, 5, 10, 15, 20, 25, 30, 35. We're increasing by 5. Number 4, 100, 81, 64, 49. What's the pattern? These are all perfect squares. So the next perfect square would be 36, 25, and 16. I wanted to take a minute and talk about perfect squares. Start with the number 1. 1 is a perfect square. And the reason it's perfect is because you can do 1 times 1 and it gives you 1. The next perfect square is 4. 2 times 2 gives you 4. So these are your perfect squares. I'm going to list them over here. The next perfect square, well, what's 3 times 3? That's 9. 4 times 4, that's 16. 5 times 5, that's 25. 6 times 6, that's 36. 7 times 7, that's 49. 8 times 8, 64. 9 times 9, 81. 10 times 10 is a 100. This list keeps going. This is a list of perfect squares. Now, what we can also do is take the square root. If I take the square root of 1, it gives me 1. If I take the square root of 4, it gives me 2. It gives me a whole number. And since it gives me a whole number, they are perfect. Square root of 9 is 3. The square root of 16 is 4. And so on. These are perfect squares in the box. If I take the square root of any of these numbers, I will get a whole number. Our learning goals for this lesson is recognize and describe patterns. Represent patterns as sequences. Predict the next term in a sequence. Represent a sequence as a table of values. Key terms that we're going to look at is a sequence, term of a sequence, infinite sequence, finite sequence. Since early elementary school, you have been recognizing and writing patterns involving shapes, colors, letters, and numbers. How are patterns related to sequences? How can sequences be represented using a table of values? Let's look at this pyramid. Pascal's triangle is a famous pattern named after a French mathematician and philosopher, Blaise Pascal. A portion of the pattern is shown. Take a moment to look at it. List at least 3 patterns that you notice. If you notice, the sides have 1. Here we have 2, a row of 3, 4, and then 6 in the middle, 5, 10s in the middle. So here we have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and so forth, and other things that we can discover. Describe how the pattern for the number of terms in each row. So if we look at this row, for example, this row has more terms than the previous row. It has 1 additional term. If we keep going, this row has 5 terms. 5 terms. This row has 4 terms. This row has 3 terms. And if we keep going, this row has 2 terms. And this row has 1 term. If we keep going in the other direction, this row has 6 terms. And this row has 7 terms. So we're adding a term to each row. Number 3, describe the pattern within each row. If you look at this pattern, especially the one in the middle, to me that seems more evident. It is symmetrical. You've got 2 in the middle and 1's on the outside. Here I've got 2 3's in the middle and 1's on the outside. Here I've got 6 in the middle. Then as we work our way out, we have a 4 and we have a 1. They are symmetrical. And you can see the same thing as it continues. Describe the pattern that results from determining the sum of each row. So if we add up the rows, well, the first row is going to give me 1. Second row is going to give me 2. The third row is going to give me 4. The next row is going to give me 8. What do you notice? The next row is going to give me 16. The next row is going to give me 32. And the next row is going to give me 64. 1, 2, 4, 8, 16, 32, 64. What's going on here? What do you notice? They're doubling each time. The sum of each row generates a pattern. So here we have another pattern. Number 5, determine the next 2 rows in Pascal's triangle. Explain your reasoning. Let's see if I can squeeze it in here down the bottom. We're going to have 1's on the outside. Notice this pattern is increasing by 1. So we're going to have 7 and 7. So we're going to write 2 rows down here at the bottom. Notice this on the edge has 1, so we're going to put those out there. This row is increasing by 1, so we'll put a 7, 7, try to form the triangle. 6 plus 15 give us 21. So we're going to have 21. 15 and 20 give us 35. And again, 35. So this row has 1, 2, 3, 4, 5, 6, 7. So this row should have 8. 1, 2, 3, 4, 5, 6, 7, 8. And then the next row, let's see, I'm going to bring that up here. 1, 7, 21, 35, 35, 21, 7, and 1. So for the next row, we want 1s on the outside. Of course, that's going to be 8 to continue that pattern. 7 and 21 gives you 28. So we'll have 28. 21 and 35 will give you 56. And then 35 and 35 give you 70. So let's see, we had 1, 2, 3, 4, 5, 6, 7, 8 numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers. Each row begins and ends with 1. All other terms are the sums of the numbers to the immediate left and right of it in the row above. The next activity, patterns to sequences to tables. A sequence is a pattern involving an ordered arrangement of numbers, geometric figures, letters, and other objects. A term of a sequence is an individual number, figure, or letter in the sequence. 10 examples of sequences are given in this activity. For each sequence, describe the pattern. Draw or describe the next term and represent each sequence numerically. Number 1, positive thinking. Analyze the number dots. Describe the pattern. Each figure has 4 fewer dots than the figure before it. If we look at this one and count up all the dots, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Has 13 dots. The one before it should have 4 more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17 dots. So the next one would have how many dots? Take 4 away from 13 and you would get 9 dots. Part B, draw the next 3 figures of the pattern. All right, so we said the next one would have 9 dots. Notice how I'm looking right here. I've got 4 above, 3 above. So I'm going to say 2 below, 1 in the middle, 2 below, 2 over here, 2 over here, 2 over there. Does that give me 9? 1, 2, 3, 4, 5, 6, 7, 8, 9. So we got 9 dots. Very messy. Not an artist. So the next one would have 4 fewer dots. So I'd have 5 dots. So let's see. I'd have 1 above, 1 in the middle, 1 below, 1 over here, 1 over there. 5 dots. Then the next one would be 4 fewer than that. So that would be 1 dot. Easy enough. I think I can draw that. 1 dot. Those are the next 3 figures in the pattern. So if you notice, we have to figure out what's going on in the pattern to predict what the next figures or numbers are going to be. Part C. Represent the figure of dots in each of the 7 figures as a numeric sequence. So, if we worked backwards, this was 1, this was 5, this was 9, this was 13, 17, 21, and 25. So 25, 21, 17, 13, 9, 5, and 1. That would be our sequence. Over here it says all numeric sequences can be represented as functions. The independent variable is the term number beginning with 1, and the dependent variable is the term in the sequence. So, let's look at that. We're going to look at these figures, and the term number is your independent. It is your domain. So this is my first drawing, this is my second drawing, this is my third drawing, this is my fourth, this is my fifth, this is my sixth, and this is my seventh. Inside the boxes below here, we're going to put how many dots we have. So in the first one, we had 25 dots. The second one, we have 21 dots. We keep decreasing by 4 dots. 17, 13, 9, 5, and finally 1 dot remains. So your term number is your X's. Your output, your Y's, are how many dots are in each term. Number 2, family tree. Jessica is investigating her family tree by researching each generation or set of parents. She learns all she can about the first 4 generations, which include her 2 parents, her grandparents, her great-grandparents, and her great-great-grandparents. Think about the number of parents. Describe the pattern. Each generation has 2 times the number of parents as the generation after that. Let's look into this. Part B. Determine the number of parents in the 5th and 6th generation. Well, in the first generation, we're going to have 2 parents to the first power. In the second generation, we're going to have 2 to the second, which will be 4 sets of parents. In the third generation, it'll be 2 to the third power, which will be 8 sets of parents. 2 to the 4th generation will be 16 sets of parents, or 16 people total. 2 to the 5th would be 32 parents, and 2 to the 6th would be 64 parents following this sequence. Part C. Represent the number of parents in each of the 6 generations as a numeric sequence. then represents the sequence as a table of value. So, let's move that over there. So for my first set, we said it was 2 to the first power. So I'll put that out here so you know what I'm referencing it to. So that gives us 2. My second term number, I said it was 2 to the second power, so that's going to be 4. My third set is 2 to the third power, which is 8. My fourth set is 2 to the fourth power, which is 16. My fifth term is 2 to the fifth power, which is 32. And then my sixth generation is 2 to the sixth power, which is 64. Let's look at another sequence or pattern. A collection of squares. Analyze the number of small squares in each figure. Describe the pattern. The number of small squares are decreasing perfect squares. So we just talked about perfect squares, beginning with square of 7. So let's look here. I've got 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So 7 times 7 gives us 49 squares. This one, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 times 6 gives us 36. So these are our perfect squares. So that's the perfect square of 7. That's the perfect square of 6. So then we would go down to the perfect square of 5, which was 5 times 5 is 25. Then we would have 4 times 4, which is 16. So these are our perfect squares. Draw the next 3 figures of the pattern. Well, let's see. We said this was 49, 36, 25, 16. So we would need a 9, a 3 by 3. Oh, here goes my art skills. So that gives us 9 squares. And then we would have a perfect square of 4. Then we would have 1 box. Part C. Represent the number of small squares in the sequence, then represents the sequence using the table of values. So in our very first box, we had 49 squares. In our second box, we had 36 squares. In our third box, we had 25 squares. In our fourth box, we had 16 squares. In our fifth box, we had 9 squares. In our sixth box, we had 4 squares. And in our last 7th box, we had 1 square. Number 4, Al's omelets. Al's house of eggs and Al's house of eggs and makes omelets. Al begins each day with 150 eggs to make his famous Best Western omelets. After making 1 omelet, he has 144 eggs left. After making 2 omelets, he has 138 eggs. My slide's a little mixed up. After making 3 omelets, he has 132 eggs left. Think about the number of eggs Al has left after making each omelet. Describe the pattern. So if you notice, we're going from 150 to 144. So he's using 6 eggs for 1 omelet. Let's see what else we can discover. Part B, determine the number of eggs left after Al makes the next 2 omelets. So let's see. He made 1 omelet and he had 140, well, he started out with 150 eggs. Then he made an omelet and it went down to 144. Then he would make another omelet and it went down to 138. Another omelet, 132. Another omelet, 126. And then another omelet, 120. So those are our next 2 omelets that he made. Part C, represent the number of eggs left after Al makes each of the first 5 omelets as a numerical sequence, then represent the sequence using a table of values. So we started this. The first term was 150 eggs. The second term was 144. The third term was 138. The fourth term was 132. And the fifth term was 126 eggs. Donna's daisies. Donna is decorating the top border of her bedroom wall with a daisy. She is applying decals, each column having a specific number of daisies. Think about the number of daisies in each column. Okay, so let's see. We got 3 daisies in that column, 4 daisies in that column, 2 daisies in that column, 3 daisies, 4 daisies, and 2 daisies. So there we have the pattern. Determine the number of daisies in the next 2 columns. Okay, so we've got 3, 4, 2, 3, 4, 2. What's going to come after 2? We're going to go back with 3 daisies, and then we're going to go with 4 daisies. Part C, represent the number of daisies in each of the first 8 columns as a numeric sequence, then represent the sequence using the table. So the sequence we've stated 3, 4, 2, 3, 4, 2. So in the first term, I've got 3 daisies. The second term, I have 4 daisies. The third term, I have 2 daisies. And then the fourth term, I have 3 daisies. The fifth term, I have 4 daisies. And the sixth term, I have 2 daisies. So in the 7th term, I'm going to go back to having 3 daisies. And the 8th term, I'm going to have 4 daisies. So 2, 3, 4, 2, 3, 4, following that pattern. Number 6, troop of triangles. Analyze the number of dark triangles. Describe the pattern. Okay, so I've got 1 dark triangle, 3 dark triangles, 6 dark triangles, and 10 dark triangles. Part B, draw the next 2 figures of the pattern. Oh, here comes my art skills. So we said 1, 3, 6, and 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the next one so in this pattern, to get 3, we added 2 more triangles. To get 6, we added 3 more triangles. No, I'm sorry, I said that wrong. I'm supposed to put the +2 with the 1. So to get the 3, we added 2, and put that in a different color. To get the 6, we added 3. To get the 10, we added 4. So if I'm adding 2, adding 3, adding 4, I need to add 5. So I need to have a triangle with 15. Oh my goodness, I don't know if I can do this. Let's see, that had 1, 2, 3, 4, so I need like 5 rows. 1, 2, 3, 4, 5. And then triangle, 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 triangle. I don't know if I can do it. Anyway, there should be 15 dark triangles. See if you can do it. This would be a dark one. 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 That's supposed to be a triangle. Let's see. So, anyway, 15 triangles. Then we would add 6 to that and get 21 dark triangles. Maybe your drawing will be better. Oh, look, they're drawn. You're welcome. Represent the number of dark triangles in each of the first 6 figures as a numeric sequence. Then represent the sequence using a table of values. So we had a sequence of 1, 3, 6, 10, 15, and 21. That's our sequence. So the first term had 1 value, or 1 dark triangle. The second term had 3 triangles. The third term had 6 triangles. The fourth term has 10 triangles, 10 dark triangles. The fifth term has 15 triangles. And the sixth term has 21 dark triangles. Gamer Guru. Micah is trying to beat his high score on his favorite video game. He unlocks some special mini games where he earns points for each one he completes. Before he begins playing the mini games, Micah has 500 points. After completing 1 mini game, he has a total of 550. Oh, my slide's messed up again. After completing 2 mini games, he has 600 points, and after completing 3 mini games, he has 650 points. So it looks to me he is gaining 50 points after each game. Part B, if you can read it in there. Remember, this is in your book. Determine Micah's total points after he plays the next 2 mini games. So let's see. We started off with 500. And he's gaining 50 points. So it'd be 550. Then he's going to 600. 650. So after 650, it'll be 700 and 750. So those are the next two. So like I said, we have to understand the pattern to predict what's going to happen next. Part C, represent it in a table. We've already done the sequence. So my first term has 500. My first term has 500. My second term has 550. My third term has 600. My fourth term has 650. And my fifth term has 700. Polygon party. Analyze the number of slides in each of the polygon and describe the pattern. So let's see, we're starting out with a triangle that has 3 sides, a square with 4 sides, pentagon with 5 sides, and a hexagon with 6 sides. Draw the next 2 figures of the pattern. Oh, awesome, my drawing skills. So imagine that you have a figure that is horrible with 7 sides, a heptagon. Then you're going to draw a stop sign, which, seriously, not an artist. 8 sides, but you get the point. Represent, oh, look at these beautiful figures that they have here. They are artists. Represent the number of sides of each of the first 6 polygons as a numeric sequence, then represent the sequence using the table. So we have 3, 4, 5, 6, 7, and 8. So my first term, I have 3 sides. My second term, I have 4 sides. My third term, I have 5 sides. My fourth term, I have 6 sides. My fifth term, I have 7 sides. And my sixth term, I have 8 sides. Pizza contest. Jacob is participating in pizza making. Each contestant has to bake the largest and most delicious pizza they can. Jacob's pizza has a 6-foot diameter. After the contest, he plans to cut the pizza so that he can pass the slices out to share. He begins with 1 whole pizza. Then he cuts it in half. After that, he cuts it in half so the slices are in half. Then he cuts those slices in half, and so on. So let's analyze what's going on here. After each cut, the slice is half the size of each slice in the previous cut. Part B, determine the size. So if he starts out with 1 whole pizza and he cuts that in half, then that would be a half. If he cuts a half in a half, that would be a fourth. If he cuts a fourth in a half, that would be 1/8. If he cuts 1/8 in half, that would be 1/16. If he cuts 1/16 in half, that would give me 1/32. So that's what you would get after 5 cuts. Part C, let's represent it in our table. So the first term, I got 1 whole pizza. Second term, half a pizza. Third term, I got 1/4 of a pizza. Fourth term, I got 1/8. Fifth term, I've got 1/32. I'm sorry, 1/16. And then the sixth cut, I've got 1/32. Coin collecting. Miranda's uncle collects rare coins. He recently purchased a rare coin for $5. He claims that the value Miranda's uncle collects rare coins. He recently purchased a rare coin for $5. He claims that the value of the coin will triple each year. So even though the coin is currently worth $5, next year it will be worth $15. In 2 years it'll be worth $45, and in 3 years it'll be worth $135. So they're already telling us the pattern. It's going to triple each year. So we're going to start out with 5. 3 times 5 gives us 15. 3 times 15 is going to give us 45, and so forth. We're going to continue with the pattern. Determine the value of the coin after 4 years and 5 years. So after 1 year, we're going to have 15, and then we're going to have 45, and then we're going to have 135, and then multiply that by 3, you're going to get $405. 405 divided by 3 gives us $1,215 after 4 years and 5 years. Part C, represent the value of coin for the table. So when we get the coin, it's worth $5. Second year, it's worth 15. Third year, it's worth 45. Fourth year, it's worth 135. Fifth year, it's worth 405. And in the 6th year, it's worth 1,215.